Welcome, friends. The voice arrives softly as if it has been waiting at the edge of the room without insisting on being noticed. Whether drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, this is a place where attention can loosen without disappearing. Before the journey begins, the voice wonders without pressure, where in the world the listening happens on an island with night air, moving through a window in a city where distant traffic becomes a steady hissy, or somewhere rural where insects and wind take turns. Wherever it is, warmth and stillness are wished into that place with no demand in return. If these slow stories bring peace or curiosity, a small gesture of liking, subscribing or sharing is mentioned as an afterthought, and gratitude is offered to those who already linger, here quietly returning. The voice turns without a pause that feels like a break toward a subject that exists whether anyone asks for it or not. The speed of light, the limit the universe enforces with perfect consistency, even though the deepest reason for the limit remains unsettled. Long before anyone names this constant Earth begins as heat and impact, and the limit is already there, built into how the universe allows influence to move. The Hadean Eon holds a planet that is not yet a stable surface, but a shifting boundary between melt and cooling crust. Rock behaves like liquid in broad regions. Impacts arrive often enough to keep the skin of the world from becoming quiet for long, and the energy of each collision is converted again and again into heat. A scientifically accepted process anchors this beginning. Earth forms by accretion, and the early planet's heat budget is dominated by the impact energy gravitational differentiation as dense metal sinks to form a core and radioactive decay from short and long-lived isotopes, all of which drive extensive melting. Only takes a few 100 million years for ground to become a temporary idea, and then the planet spends longer trying to make it permanent. In the Bolton brightness, light is not decoration. It is one of the main ways the planet begins to cool. Hot surfaces emit thermal radiation infrared photons that carry energy away into space, and this radiative loss becomes a quiet, relentless accounting. A planet can cool by convection and by conduction within itself, but to shed heat to the wider universe it must radiate, and radiation travels outward at a finite speed. The accepted fact is simple, and large electromagnetic radiation propagates in vacuum at the speed of light, and the energy Earth loses, as heat leaves as photons that do not arrive everywhere at once. They stream outward, crossing space over time. Only takes the absence of a medium for light to move at its special pace, and then the pace becomes a rule that no engineering can exceed. A poetic detail lives in the Hadean glow, even without an eye to see it. The surface can shimmer where thin crust forms and breaks, where fresh lava skins over and then fractures, revealing brighter melt beneath. The glow is not a single colour. It is a spectrum governed by temperature shifting toward longer wavelengths, as the planet cools, as if Earth learns gradually to dim itself. The photons that leave carry the signature of that temperature in their distribution, meaning the planet's heat is written into the light it emits. Only takes a hot body to broadcast its condition into space without intending to communicate. Here the speed limit enters in the least dramatic way. It makes cooling a process that cannot be instantaneous. Not because the planet wants to cool slowly, but because the universe allows energy to leave only by mechanisms that have finite rates. Even if the surface could radiate infinitely intensely, the energy would still be carried away by photons that must travel outward. Space does not swallow heat in one mouthful. It receives it as an outward flow. This is one of the section's soft ironies. The universe provides a limitless void for heat to escape into, yet it insists the escape occurs at a fixed pace, as if infinity is patient by policy. Another irony follows. The speed of light is sometimes imagined as a property of light alone, Yet it is also the speed limit for causality in modern physics. So a beam of light becomes the ruler by which the universe measures what too fast means for everything. A third irony rests gently behind them. Early Earth is violently energetic, yet the most consistent governor of that energy's departure is a quiet constant, a number that never flinches no matter how bright the magma becomes. Only takes a constant to ignore drama. The atmosphere of this young world is not a modern sky. It is built from outgassing and impact-generated vapor rich in water vapor and carbon dioxide, with nitrogen present and oxygen scarce as a free component. The sky can be thick, hazy, and variable, filled with dust from impacts and aerosols from volcanism. These gases matter for cooling because they absorb and re-emit infrared radiation, shaping how efficiently heat can escape. The greenhouse effect is not a modern invention. It is a consequence of molecular absorption spectra, and those spectra depend on quantized energy levels in molecules. Yet even as gases slow the escape of heat, the heat still leaves only by radiation that travels at the speed of light once it is emitted into space. Only takes a molecule with the right vibrational modes to hold warmth a little longer. The quiet scientific mystery in this first section is not whether the speed of light exists or whether it is measured. Those are settled, but why this particular limit exists as a fundamental feature of the universe. In modern physics, the speed of light appears as a constant that links space and time in relativity, arising from the structure of spacetime and from the invariance of physical laws for all inertial observers. Yet the deeper reason that the universe has this invariant speed at all, and why its value is what it is, rather than something else, is not answered in a way that feels final. Some descriptions treat it as a conversion factor between units, others seek deeper unification, but the underlying why remains a quiet gap behind the certainty of it is. Only takes a perfectly consistent rule to invite a question that cannot be dismissed. Earth still molten does not care about the question, it responds only to the rule. Heat rises, crust forms and fails, metal sinks, vapor condenses and re-evaporates. The moon may be forming nearby through a giant impact scenario itself, a subject with uncertainties of mixing and timing, but the speed at which light travels between Earth and any nearby debris is already fixed. Even the distance to the young sun and the time its light takes to arrive is already a matter of minutes rather than instant presence. The sun shines and Earth receives that radiation after a delay set by the speed limit, then returns energy as infrared after its own delay set by absorption and re-emission. Cause and effect are already separated by travel time even in the earliest eon. Only takes space between objects for time to become part of every interaction. The section lingers on the feeling of a constant hovering above a molten world. Light leaves the surface and does not return. Sunlight arrives and does not arrive faster because anyone wishes it. The limit is not a barrier seen in the sky. It is a property of how the universe stitches events together. Earth begins in fire and the rule is already in place, indifferent, steady and unexplained in its deepest origin, yet utterly dependable in its effects. The Hadean world continues to lose heat in ways that feel both relentless and restrained, as if the planet is allowed to cool, but never allowed to do so in a hurry. A crust forms, breaks and reforms, sometimes as thin rafts over magma, sometimes as thicker patches that survive long enough to be altered by rain and impact. Above, the atmosphere shifts between heavy vapor and clearer intervals depending on temperature and bombardment, and the boundary between air and space remains a gradient rather than a wall. In this setting, light becomes the main courier of change, not because it creates the changes on its own, but because it is how energy and information move between Earth and the rest of the cosmos. A scientifically accepted process anchors the section's core. Visual radiative heat transfer governs how a hot planet cools to space, and the spectrum of emitted radiation depends on temperature, while atmospheric gases can absorb and re-emit infrared, shaping the effective rate of cooling. Only takes a hot surface to shine in wavelengths invisible to eyes, and it takes an atmosphere to decide how easily that sheen escapes. The speed of light sits inside this process as a quiet limiter. Photons do not teleport energy out of a system, they carry it, and carrying implies travel. The planet's emitted infrared leaves in a stream that expands outward, thinning with distance, crossing the growing emptiness between Earth and every other object. Even if nothing intercepts it, it still requires time to move away. This seems obvious in the modern mind, but the section lets the obviousness relax into something stranger. The universe could have allowed instantaneous action at a distance in principle, and yet it does not. The radiated heat from Hadean lava is not everywhere at once. It becomes part of a light cone, a region of spacetime that can be affected, expanding at a fixed speed. Only takes a single emission event for causality to take on a geometric shape. A poetic detail rests in the way impact dust changes the look of day. After a significant collision, fine particles can remain suspended and spread globally, scattering sunlight and altering how much energy reaches the surface. In the Hadean, such events are frequent enough that the sky can shift from bright to dim and back again, a planet-scale filtering that does not require seasons. The dust itself is made of rock ground to powder and vapour condensed back into solids, and it hangs in the air like an unasked-for veil. Only takes a distant collision to change the brightness of a noon that has no observers. The sun continues to shine, and Earth continues to receive its light after a delay set by distance and the universal limit. The light that arrives is not only energy, it is information about the sun's state a few minutes earlier, about its surface temperature, about its spectrum, about its variability. Even in the early solar system, the young sun is more active in high-energy radiation than it is later, with stronger ultraviolet and particle emissions associated with a more magnetically active star. That activity reaches Earth not as instantaneous influence, but as arriving bursts, each one travelling across space at finite speed. A scientifically accepted fact is quiet here changes in electromagnetic conditions and radiation propagate at light speed in vacuum, so any variability in the sun is experienced on Earth after a travel time and never sooner. Only takes a flare for the universe to demonstrate delay as a built-in courtesy. 3 soft ironies settle into this section, spaced out like slow breaths. First, the sun is the dominant energy source for Earth's surface in the long run. Yet Earth experiences the sun slightly in the past, always receiving news of the star as it was minutes ago. As if even the closest cosmic relationship is forced to be late. Second, Earth's hottest early moments emit the most radiation, yet the energy still leaves by the same rule and the same speed, so brilliance does not buy priority. Third, the atmosphere both protects and delays. It can shield the surface from some incoming radiation and trap some outgoing heat, yet it cannot change the speed at which light itself travels once free, meaning the planet's blankets are powerful but never magical. Only takes a greenhouse gas to keep a surface warmer, while leaving the cosmic rule untouched. As cooling continues, water begins to take on a different role. At high temperatures, it exists mostly as vapor. As temperatures drop, condensation becomes possible and rainfall begins. The formation of oceans is not a single moment but a threshold crossed and recrossed, with impacts and volcanism sometimes returning water to the air and cooling sometimes bringing it back down. A scientifically accepted process sits under this. Water vapor condenses when temperature and pressure allow, and liquid water can persist when the surface and atmospheric conditions keep it within the stability range. The uncertain part remains in the details: how quickly oceans become stable, how often they are vaporized again by late impacts, and how much water is delivered versus retained. only takes one large impact to rewrite a hydrosphere's phase, and it takes long intervals of relative quiet for water to settle into basins. Light threads through this story as both heater and messenger. Sunlight arrives, warms the surface and drives evaporation. Infrared leaves cooling the planet. Both journeys are constrained by the same limit and both set the pace at which surface conditions can respond. There is no instant warming and no instant cooling across a planet's surface. There are only transfers, delays, and redistributions. The section lets this linger. Even in a small room, warmth travels at finite speeds through air and walls. On a planet, the same principle expands, mediated by radiation, convection, and circulation. Only takes a planet-sized distance for the idea of later to become part of every physical process. The quiet scientific mystery in this section returns to the central question in a new angle. Relativity makes the speed of light an invariant feature of spacetime, and Maxwell's equations in electromagnetism predict a characteristic propagation speed for electromagnetic waves in vacuum. Yet the deeper origin of why spacetime has this invariant structure remains an open foundational curiosity. Physics can describe consequences with exquisite success. Time dilation length, contraction, causality constraints, but the underlying why this structure and not another remains a place where explanation often becomes a matter of deeper theory choices and unit conventions rather than a single satisfying cause. Only takes a rule that is everywhere to feel like it ought to have a reason that is equally everywhere. Earth continues without waiting for the reason. Its surface cools by radiating. Its atmosphere thickens and thins. Water rains and gathers, then steams and gathers again. Each change is experienced locally first and then spread by winds and currents, but the first mover for much of the surface energy is radiation that arrives and departs at a fixed speed. The planet is already living inside a causal structure, already moving through time with constraints, already receiving and emitting energy in delayed streams rather than instant exchanges. The Hadean looks chaotic, yet it is governed by a constant that never wavers. The speed limit does not explain itself, but it explains the shape of all changes by enforcing that no change arrives without travel. The planet begins to hold water more reliably, and with that holding comes a new kind of patience. Steam is still present, and volcanism still supplies vapor, but the surface spends longer intervals below the temperatures that force oceans back into the air. Rain becomes less episodic and more like a slow habit. Basins fill and remain filled. The ocean's surface forms a moving boundary that reflects some sunlight and absorbs the rest, then returns energy upward as infrared. A steady exchange that never becomes instantaneous. A scientifically accepted process anchors this section. Earth's surface energy balance is governed by incoming solar radiation, reflected energy determined by albedo, and outgoing infrared emission, with greenhouse gases modulating how easily heat escapes, and because energy transport is finite, the system responds with lags rather than immediate equilibrium. Only takes a few degrees of change in radiative forcing for an ocean to adjust over time instead of at once. Here the theme of no instant heat becomes literal. Sunlight crosses space at the speed of light and arrives delayed by distance. Then upon reaching Earth, its energy does not instantly become global warmth. It must be absorbed by her ocean water or rock, converted into molecular motion, and then redistributed by convection winds and currents. Even the radiation that leaves again emitted as infrared from the surface and atmosphere does not instantly cool everything. It is emitted from particular places at particular times and then travels outward. The planet's warmth is therefore a moving pattern, not a uniform field. Only takes a rotating sphere and a finite signal speed for day and night to become a migrating boundary rather than a switch. A poetic detail rests in the newborn ocean's first textures. Where lava meets water, it cools rapidly and forms pillow basalts, rounded bulbous structures created when molten rock quenches in seawater, developing glassy skins that crack and inflate as new lava pushes through. These shapes, preserved later in ancient rock sequences, become quiet proof that liquid water exists at the time of eruption. The pillows look almost soft in silhouette, as if rock learns to imitate fluid forms. Only takes cold water touching hot basalt for stone to freeze into a memory of its own flow. The early oceans also begin to store heat and release it slowly. Water's high heat capacity means that large bodies of liquid resist rapid temperature change, smoothing the planet's daily and seasonal swings in any era where seasons exist, though the early Earth's rotation and atmospheric conditions differ from modern. Heat absorbed in one region can be carried by currents and released far away, a slow redistribution that does not need instantaneous transfer. This is one of Earth's long lessons. The most important transports are often slow, and their slowness is a feature, not a failure. Only takes an ocean to turn energy into a delayed consequence. The speed of light is not only about photons in vacuum, it becomes a boundary for how quickly any influence can propagate through spacetime. Yet within Earth's environment, other speed limits emerge that are slower. Sound travels through air and water at finite speeds set by the medium's properties. Thermal conduction carries energy through rock far more slowly. Ocean currents carry heat even more slowly, measured in meters per second at best and often far less. The planet becomes a layered hierarchy of delays, the universal limit above and a set of local limits below, each one turning cause into an effect that arrives later. A scientifically accepted fact sits under this hierarchy. Energy transport occurs through radiation conduction and convection, each with characteristic timescales and propagation behaviors, and none provide instantaneous action. Only takes a medium for fastest possible to become something much slower than light. Three soft ironies settle across this layered delay. First, sunlight is unimaginably fast compared to winds and currents. Yet from the perspective of a warming ocean, the arrival of photons is the quick part. The slow part is the water's response, so speed can be irrelevant when storage dominates. Second, people later think of the speed of light as a limit that makes the universe feel large and lonely. Yet on early Earth, the more pressing loneliness is not between stars, but between regions of the same planet that cannot share heat quickly enough to behave uniformly. Third, oceans form as a stabilizing presence, yet they do so by delaying change, by absorbing and releasing energy slowly. So calmness is achieved by refusing to respond promptly. Only takes a reservoir to turn urgency into lag. The quiet scientific mystery in this section rests in a deceptively simple place. The early climate's balance remains hard to pin down. The faint young sun problem still hovers, and while greenhouse gases and atmospheric composition likely provide warming, the exact roles of carbon dioxide, methane clouds, haze, and surface albedo are not fully settled for the earliest ocean-bearing Earth. Proxy evidence is sparse and altered. Models depend on assumptions about volcanic outgassing rates, ocean chemistry, and atmospheric photochemistry under strong ultraviolet light. The uncertainty persists not because the system is unknowable, but because the inputs are ancient and the record is incomplete. Only takes 4 billion years of recycling to make a planet's earliest thermostat hard to read. As the ocean becomes stable, it interacts with the crust in a new continuous way. Hydrothermal circulation begins to thread seawater through hot basalt, altering the rock and changing ocean chemistry, while also moving heat from the crust into the ocean. This is a scientifically accepted process. Seawater circulating through newly formed oceanic crust exchanges elements, and heat-producing altered minerals and vent fluids that influence the composition of seawater. The ocean is not a passive pool, it is a chemical participant, and its participation is powered by heat that ultimately must leave the planet by radiation. Only takes a crack in basalt for an ocean to begin circulating through the planet's skin. The speed of light remains the distant limiter of this entire exchange. The planet's heat must eventually be radiated away, and that radiation leaves at the same fixed speed regardless of how slowly the interior supplies it to the surface. This creates a subtle asymmetry. The universal exit route is fast, but the internal delivery is slow, so the planet's cooling rate is set not merely by how quickly it can shine, but by how quickly heat can reach the shining surfaces, and by how the atmosphere regulates the escape. Only takes a thick atmosphere to make fast radiation feel slow at the surface. A gentle modern analogy appears briefly and then fades. Earth's early ocean behaves like a massive thermal ledger, taking deposits of solar energy during the day and making withdrawals at night, smoothing the balance so the surface does not swing wildly. The analogy remains restrained because the physics is already clear. The ocean's calmness is not magic, it is heat capacity and transport. The section ends with the feeling that the planet's first stable waters do not merely add a new substance to the surface, they add a new timescale. Water delays, stores and redistributes. It makes the planet's energy story less abrupt. And above it all, the speed of light remains the quiet constraint that ensures every warming, every cooling, every radiative exchange happens as a sequence rather than a simultaneous condition. Earth's earliest oceans are born into a universe where even heat must travel, and they quickly become experts in making travel slow on purpose. Deep inside the young planet, the separation of metal from rock continues to matter long after the first dramatic sinking has finished. The core is not only a reservoir of dense iron, it is a moving convecting region whose behavior shapes the space around Earth in ways no surface wave can imitate. In the Archean, the interior remains hotter than in later times, and the mantle above the core circulates with the vigour tied to that heat-feeding volcanism and renewing the crust. A scientifically accepted process anchors the section motion of electrically conducting fluid in Earth's outer core, powered by heat flow, and compositional buoyancy sustains a geodynamo that generates a global magnetic field, and that field shapes a magnetosphere that interacts with the solar wind, guiding charged particles and influencing atmospheric escape pathways. Only takes a rotating ocean of liquid metal for a planet to invent an invisible architecture. The magnetosphere is not a rigid shell. It is a shaped region of space formed by the balance between Earth's magnetic field and the flowing plasma from the Sun. On the day side, it is compressed. On the night side, it is stretched into a long tail. In the Archean, with a more active young sun, the pressure and variability of the solar wind are likely stronger, meaning Earth's magnetic environment is more agitated, more frequently reconfigured by incoming streams of charged particles. Yet even in agitation, the rules remain: disturbances in electromagnetic fields propagate at the speed of light, and changes carried by the solar wind arrive, after crossing interplanetary space at finite speed slower than light for the particles themselves, but constrained by the same causal structure. A scientifically accepted fact sits quietly here. Electromagnetic signals and field changes propagate no faster than light, and plasma interactions remain causal, so the magnetosphere responds to solar wind conditions after they arrive, not before. Only takes space between star and planet for shielding to become a timed negotiation rather than a constant state. A poetic detail lives in a region that has no direct eyewitness in deep time, the auroral zones where charged particles spiral along magnetic field lines and collide with atmospheric atoms and molecules producing light. In the modern world, auroras paint curtains of green and red across polar skies. In the Archean, the exact colours and intensities depend on atmospheric composition and solar activity, but the basic physics remains excitation and emission, a dance of electrons in atoms returning to lower energy states by releasing photons. The thought is not romanticized. It is simply placed gently. Even in a young, harsh sky, there are moments when energy arriving from the sun is turned into faint light in the upper atmosphere, a quiet reminder that the planet's space environment is active. Only takes a collision at the top of an atmosphere to make a photon that falls downward. The speed of light becomes a limit in this story in two intertwined ways. First, it is the speed at which electromagnetic information moves the restructuring of fields, the propagation of radio waves, the movement of causal influence in the equations of electromagnetism and relativity. Second, it is the speed that sets how quickly any action can be known elsewhere, making shielding not an absolute wall, but a dynamic, time-dependent response. The magnetosphere cannot anticipate, it can only react. The solar wind cannot influence Earth instantly, it must travel. The aurora cannot flicker before particles arrive. Only takes the rule of causality to turn every interaction into a sequence. Three soft ironies settle into this section. First, the magnetic field is often spoken of as protection, yet it is produced by constant motion and dissipation in the core, meaning Earth's safety feature is powered by perpetual internal unrest. Second, the magnetosphere is an invisible structure that reaches far into space, yet its shape can be compressed and stretched by a wind that is itself invisible. So two unseen things negotiate boundaries that determine how much atmosphere can be eroded. Third, the speed of light is sometimes imagined as the fastest messenger yet in the space around Earth. The most dramatic arrivals come as slower streams of particles that take days to cross from Sun to Earth, while the information about electromagnetic disturbances can propagate faster, so the warning can outrun the storm, at least in principle. Only takes a difference between particle speed and signal speed for the universe to allow foreknowledge without prevention. Earth's atmosphere during the Archean remains chemically reducing compared to the modern world, and its upper layers are vulnerable to escape, especially for light species like hydrogen. Magnetic shielding helps, but it does not eliminate escape, and the details depend on solar activity, atmospheric composition, and the strength and geometry of the field. The uncertainty is quiet but real. How strong is Earth's magnetic field in the early Archean? How stable is it, and how much does it reduce atmospheric loss compared to an unmagnetized planet under the same solar conditions? Paleomagnetic evidence from ancient rocks suggests the presence of a field early, but the record is sparse and contested, and interpreting it requires caution. Only takes a few surviving minerals with remnant magnetization to carry a hint of a field that once wrapped the planet. The section's scientific mystery then rests not only in the deep why of the speed of light, but in the practical archaeology of the early magnetosphere. The planet's shielding architecture likely exists, yet its early history is difficult to reconstruct with confidence. Even in modern times, magnetospheric dynamics are complex. In deep time, the constraints are indirect. The story allows the uncertainty to remain as it is like a region of night-side tail, stretched beyond the reach of easy measurement. Only takes an incomplete record for the most important invisible structure to remain partly unknown. A gentle modern analogy appears briefly and then fades. The magnetosphere resembles a wake around a moving ship, shaped by the flow it meets, except the ship is Earth, and the water is plasma, and the wake is made of fields. The analogy is limited, and the section returns to the physical reality of field lines, charged particles, pressure, balance, and propagation delays. The limit of light speed also touches the core more subtly. The core's convective motions are local, and their changes communicate through mechanical and electromagnetic processes that have finite speeds. Nothing inside Earth updates instantly either. Seismic waves, electromagnetic diffusion, and thermal conduction all impose timescales. Yet the cause-consequences reach outward to space through the magnetic field, and that reach is bounded by the same causal rule as everything else. The planet's interior and the solar wind meet in a space where no message travels faster than light, and the resulting boundary is a living shape that changes with time. Earth continues to rotate beneath that boundary, and the rotation itself is a kind of steady clock, though not perfectly constant over billions of years. Day length changes as the moon's tides exchange angular momentum with Earth's spin, another slow communication of influence that respects delays and dissipation. The magnetosphere, too, is part of this slow planetary communication, a link between deep liquid metal and the space above, mediated by electromagnetic fields that propagate at a fixed speed while being shaped by flows that are slower. The section lingers on this layered system core field plasma atmosphere, each level connected, each connection limited, each limit making the planet's protection a process rather than a state. The speed of light remains the quiet rule that ensures the shield is never instantaneous, only always arriving. The sky becomes a book written in gaps. It is not the visible blue or grey that matters most, but the specific wavelengths that never reach the ground, absorbed and re-emitted by molecules that keep their own quantum rules. In the Archean, the atmosphere is still unlike the modern one, yet it already behaves as a selective filter. Certain frequencies of light pass easily, others are detained, and the detention changes the planet's temperature, chemistry, and long-term evolution. A scientifically accepted fact anchors the section atoms and molecules absorb and emit electromagnetic radiation at specific energies corresponding to quantized transitions, producing spectral lines and bands that govern radiative transfer in atmospheres. And these absorption features are fundamental to greenhouse warming and to the cooling of a planet to space. Only takes an electron's allowed energy levels to decide what parts of starlight and infrared can travel freely. This selectivity makes the speed of light feel less like a simple number and more like a law with texture. Photons may travel at the same speed in vacuum, but in an atmosphere they are repeatedly absorbed and re-emitted, or scattered, turning a straight flight into a zigzag of delays. The photon still moves at light speed between interactions, yet the effective transport of energy becomes slower because the path becomes longer and interrupted. In the language of radiative transfer, optical depth matters. A thick greenhouse atmosphere can make outgoing infrared photons take many interactions before escaping to space, delaying cooling. The accepted process remains calm and precise. Greenhouse gases absorb infrared and re-emit it in random directions, increasing the residence time of heat in the lower atmosphere and surface system. Only takes a few strong absorption bands for a planet to hold warmth far longer than bare rock would allow. A poetic detail lives in the idea that the planet's warmth is not held like a blanket held still. It is held like a conversation of photons that keep being interrupted. An infrared photon emitted from a warm surface may travel a short distance, be absorbed by a carbon dioxide molecule, and then be re-emitted upward or downward or sideways in a new direction, as if the energy keeps trying to leave and keeps being asked to repeat itself. The process is mechanical and statistical, not intentional, yet the effect is persistent. Only takes a dense enough atmosphere for escape to become a slow negotiation rather than a quick departure. This is where the section's theme of the speed limit deepens. The speed of light sets the maximum speed for each step of a photon's travel, but the atmosphere sets how many steps are required. It is a reminder that a universal limit does not guarantee universal quickness. Earth can be warmed not by slowing light itself, but by forcing light to take detours, The planet does not break the rule. It uses the rule's own patience. Only takes a few molecules with the right vibrational modes to turn a cosmic constant into a long delay. 3 soft ironies settle into this photon bookkeeping. First, the speed of light is often treated as the fastest thing yet. In an atmosphere, it becomes easy to trap energy for long times, meaning fast is only meaningful when the path is simple. Second, the greenhouse effect is sometimes described as if it is an added feature, yet it is simply the consequence of quantum selection rules in molecules, so climate is shaped by the same discretization that shapes spectroscopy. Third, early Earth's atmosphere can make the faint young sun sufficient for liquid water by trapping heat, while later humans spend effort trapping light in fiber optics and cavities for experiments, as if both planet and laboratory discover that confinement is a powerful tool. Only takes a container to turn speed into waiting. The Archean sky likely contains abundant carbon dioxide and nitrogen with water vapor, varying with temperature and location. Methane may also be present depending on sources from geology, and if life is established from microbial activity. Methane's greenhouse effect can be strong, but methane is also subject to ultraviolet breakdown, and its photochemistry can produce organic hazes that reflect sunlight and cool the surface while shielding ultraviolet. The quiet mystery here is real and specific, the exact composition of the Archean atmosphere, including methane levels, and the prevalence of haze remains uncertain and contested because the evidence is indirect, encoded in isotopes, paleosol, sediment chemistry, and models of photochemical reactions under a young sun. The faint young sun problem sits behind this uncertainty, and its resolution likely involves multiple factors rather than one simple gas concentration. Only takes one missing constraint to keep a climate reconstruction open. The speed of light appears again as the carrier of information in spectral lines. Sunlight arriving at Earth carries the signature of the sun's surface temperature and composition encoded in absorption lines in the solar spectrum. Earth's atmosphere modifies that spectrum, again imprinting its own absorption features. In modern science, these imprints become the basis for remote sensing by measuring which wavelengths are missing, or weakened scientists infer the presence and abundance of gases. The accepted fact is quiet and profound light carries information through its spectrum, and that information cannot travel faster than light itself. The universe ensures that knowledge is delayed, always arriving after the source has already been what it was. Only takes a finite propagation speed for every observation to be a look into the past. Earth's early atmosphere then becomes a kind of unrecorded spectrum. It shapes the planet's energy balance and chemistry, but few direct traces remain, so the spectrum must be inferred long after the photons are gone. Rocks become the proxy for missing light-preserving chemical consequences. Certain sulfur isotope patterns can indicate an atmosphere with extremely low oxygen because mass-independent fractionation processes in sulfur occur under ultraviolet photochemistry in an oxygen-poor environment and are later erased when oxygen rises and ozone blocks the relevant ultraviolet wavelengths. This is an accepted line of evidence for atmospheric change, and it is also a reminder that the atmosphere's spectral properties shape what photochemistry is possible. Only takes ozone to remove a pathway, and the isotopes change accordingly. A gentle modern analogy appears briefly and then fades. The greenhouse atmosphere behaves like a hallway of mirrored doors, where light can move quickly between doors but still takes a long time to find the exit because it keeps being redirected. The analogy remains restrained and then dissolves back into the real physics of absorption and emission. The section's central uncertainty returns to the deeper question of the speed limit itself. Maxwell's equations in vacuum predict a propagation speed for electromagnetic waves, and relativity elevates this speed to an invariant boundary for causality. Yet the reason the universe has this invariant structure remains a foundational question. Some perspectives treat it as a geometric property of spacetime, others as a symmetry statement about the laws of physics, and the numerical value depends on unit conventions. Yet the existence of a finite invariant speed remains an unexplained bedrock fact in the sense that physics describes it rather than derives it from something simpler that is universally accepted. Only takes a bedrock fact for all of physics to build upon it, and still wonder what the bedrock rests on. Earth's sky continues to filter and delay. Oceans continue to absorb and store. The planet's cooling continues to be governed by how efficiently infrared can escape through those spectral gaps and bands. Light moving at its limit between interactions becomes slowed in effect by repeated capture, and the planet's climate becomes a story of detours. The speed of light remains constant and the world's temperatures still change slowly, proving again that the universe can be governed by fast rules while living out slow consequences. The Archean Ocean does not need to be violent to be powerful. It is enough that it is vast-layered and never fully still. Its surface receives sunlight, its depths receive heat from the crust, and between them water moves by gradients that are patient and persistent. Temperature differences, salinity differences, and the planet's rotation shape currents that carry warmth and dissolved chemistry across distances no single storm can cross in a day. This slow transport becomes a second speed limit layered beneath the universal one, reminding the planet that even if light arrives quickly, the consequences can spread slowly through matter. A scientifically accepted process anchors the section ocean circulation transports heat and dissolved substances through advection and mixing. And because these processes are finite and often slow, Earth's climate and chemistry respond with time, lag smoothing and delaying changes, rather than reflecting them instantly. Only takes a density gradient for water to become a long messenger. The speed of light remains the boundary for the fastest possible communication, but Earth's living surface is governed more often by slower communications currents, winds, and diffusion. A parcel of warm surface water can drift cool sink and travel for years or centuries before returning, depending on the circulation pattern. The details of Archean circulation are uncertain because the ocean basins, continental configurations, and atmospheric conditions differ from modern, yet the principle is stable. Large fluids distribute energy over time, and time becomes part of climate. Only takes an ocean's volume for immediate to become a meaningless expectation. A poetic detail rests in the way the ocean hides movement. From above, a surface can look like a simple plane reflecting sky, but beneath it there are internal waves travelling along density layers and slow eddies turning quietly and upwelling and downwelling that exchange deep water with surface water without drama. In the Archean, with warmer temperatures and different chemistry, the layering and buoyancy relationships may differ, but the sea remains a stacked system in which motion can be subtle and continuous. Only takes stratification for energy to move without obvious surface change. Relativity's causal structure is introduced here with a gentle firmness, not as a lecture, but as a backdrop to why Earth slow transports matter. In special relativity, the speed of light in vacuum is the same for all inertial observers, and it acts as the maximum speed at which information and causal influence can travel. This is not merely about light, it is about the geometry that links space and time. A scientifically accepted fact is quiet here. No object with mass can be accelerated to the speed of light in vacuum, and no signal carrying usable information can propagate faster than light, preserving causality in relativistic physics. Only takes one invariant speed for the universe to draw a clear boundary around too fast. Earth, though, spends most of its history far below that boundary. The ocean's speed is slow, and the atmosphere's speed is modest, and the crust's speed is slower still. These slower speeds matter because they are the ones that shape habitability. How quickly heat can be shared between equator and poles, how rapidly gases can be mixed, how long chemical gradients can persist. The contrast is a calm kind of humour. The universe provides an ultimate speed limit, and the planet responds by making most important processes move at a pace that is almost leisurely. Only takes a rotating sphere with viscous fluids for urgency to be optional. 3 soft ironies settle into this layered system. First, the speed of light is often treated as the reason the cosmos feels distant yet. Earth's own ocean currents can make the planet feel distant from itself, connecting regions only over long times. So separation is not only cosmic, it is terrestrial. Second, humans later build communication networks that move information near light speed, yet the ocean continues to move heat and carbon at its old pace, as if the planet does not notice technological impatience. Third, relativity forbids faster than light messages, yet Earth's most consequential messages, climate shifts, chemical transitions, tectonic rearrangements, are delivered at speeds so slow they hardly qualify as messages at all until long after they arrive. Only takes deep time for cause and effect to look like separate eras. The section's quiet scientific mystery rests in the interplay between early ocean circulation and the faint young sun problem. The ocean's ability to transport heat could help moderate regional climates, but without knowing basin geometry, atmospheric composition, cloud behavior, and rotation rate details with precision, it remains difficult to determine how much circulation contributes to keeping surface water liquid in different latitudes. The Archean world may have fewer large continents and more ocean coverage, which could affect albedo and circulation patterns, yet the reconstructions are uncertain. Only takes one unknown coastline to make an ancient current map speculative. In the ocean, chemical transport is as important as heat. Dissolved iron, silica, and other ions move with currents and with hydrothermal inputs. In an anoxic sea, iron can remain soluble, and its distribution depends on mixing and sources. Hydrothermal vents inject reduced chemicals and heat, and those injections spread along density layers and through turbulent mixing. A scientifically accepted process sits under this hydrothermal circulation. Exchanges seawater with hot crust, altering chemistry and supplying nutrients and reduced compounds to the ocean, and ocean mixing distributes these compounds, influencing sediment formation and potentially early ecosystems if life exists. Only takes a vent to create a chemical plume that travels farther than the vent itself could ever reach. The speed of light remains present as the ultimate limiter even when not directly relevant. Sunlight drives surface heating and photochemistry, and those photons arrive quickly compared to currents, but once their energy becomes heat in water, its redistribution is governed by fluid mechanics. The planet demonstrates in a steady way that fast inputs can produce slow outputs. This is not inefficiency, it is storage and transport. The ocean becomes a buffer that turns rapid day-night cycles into smoother thermal fields, and it turns episodic volcanic inputs into long-lived chemical reservoirs. Only takes mass and mixing for time to become part of chemistry. A gentle modern analogy appears briefly and then fades. The ocean behaves like a slow conveyor belt carrying warmth and dissolved salts, not in a single belt, but in many overlapping loops, each one taking its own time. The analogy is kept small because the real physics is already clear. Density differences, Coriolis effects from rotation wind stress, and basin geometry shape circulation. Relativity's limit also introduces a subtle conceptual stillness. Because no influence is instantaneous, the universe is stitched together by delays. Even within Earth's ocean, nothing updates everywhere at once. A change in surface temperature is not instantly known in the deep sea. it must propagate through mixing and waves. In the atmosphere, pressure disturbances travel as sound waves. In the crust, stress changes travel as seismic waves. The speed of light sits above them all as a ceiling, but Earth lives mostly in the slow domain beneath. The planet's stillness in deep time is built from these delays. A system that takes time to respond is a system that can maintain gradients long enough for structured processes to occur. Only takes finite speeds for the world to avoid collapsing into instant uniformity. The section ends with the sense that the ocean is one of Earth's greatest teachers of the speed limit's meaning. The universe's fastest messenger brings energy and information, but the ocean decides how that energy becomes climate and chemistry, and it does so with lags that are not errors but features. The speed of light remains the outer boundary of causality, and the Archean Ocean remains the inner boundary of patience, a vast reservoir that turns even a swift photon into a slow planetary consequence. The young sun does not simply shine, it behaves. It turns, it stirs its magnetic fields, and it releases bursts of energy and particles that are more frequent and intense in its youth than in its quieter maturity. Earth, still early in its own history, receives these changes not as immediate commands but as arrivals, each one crossing the space between star and planet with delays that are smaller in human terms and enormous in the arithmetic of cause and effect. In the Archean, those arrivals meet an atmosphere without an ozone shield, an ocean already present, and a magnetosphere that shapes which charged particles reach the upper air. A scientifically accepted fact anchors the section. The early sun is expected to be more magnetically active, producing stronger ultraviolet emission and more frequent energetic particle events. And these outputs influence planetary atmospheres through photochemistry and atmospheric escape processes, with effects that occur only after radiation, and particles traverse interplanetary space. Only takes a young star to make space weather a persistent part of a planet's environment. Ultraviolet light arrives first in relevance. It travels at the speed of light reaching Earth after a short delay set by the orbital distance, then penetrating more deeply than it does in later eras, because ozone is not yet present in significant amounts. In an oxygen-poor Archean atmosphere, ultraviolet photons can break apart molecules, driving photochemical reactions that reshape gases like methane, water vapor, and carbon dioxide derivatives. The chemistry does not happen all at once. It occurs where photons are absorbed, where radicals are produced, where the chain reactions are sustained. The accepted process is clear photodissociation. By ultraviolet radiation initiates atmospheric chemical networks producing and destroying species, and sometimes generating aerosols that alter atmospheric opacity. Only takes a single energetic photon to break a molecular bond, and then the consequences spread through chemistry at slower speeds. A poetic detail rests in the high sky where these reactions occur. The upper atmosphere is thin enough that molecules can travel farther between collisions, and sunlight can create regions where chemistry is driven by radiation rather than by thermal equilibrium. In modern terms, it is a place where day can mean a different chemical regime than night, and where the boundary between atmosphere and space feels porous. In the Archean, that porosity likely matters for hydrogen escape because water vapor broken by ultraviolet can produce hydrogen that can escape more easily than heavier species. Only takes a light atom to find a path out of a weakly held upper air. The speed of light appears again as the carrier of a warning that cannot prevent what it warns about. Electromagnetic disturbances and radiation arrive quickly, but the particles of the solar wind and of energetic events travel more slowly, typically at hundreds of kilometers per second for the bulk wind and faster for some energetic particles, yet still below light speed. This creates a layered arrival. Information in radiation can precede the bulk particle arrival, and changes in solar conditions are experienced as sequences rather than instantaneous shifts. A scientifically accepted fact sits quietly here. Solar wind and coronal mass ejections involve plasma traveling at finite speeds far below light speed, and their interaction with planetary magnetospheres and atmospheres occurs after transit times that can range from minutes for some energetic particles to days for bulk plasma structures. Only takes a difference in speeds to make a planet's space environment feel like a series of waves rather than one event. 3 soft ironies settle into the section's star-planet relationship. First, the fastest messenger light brings the energy that can break molecules and reshape chemistry, yet it cannot be outrun by any warning because it is the warning, meaning the planet learns about the disturbance only by being disturbed. Second, the sun's activity makes Earth's atmosphere more chemically dynamic, yet the planet's long-term stability relies on slow feedback, so rapid variability sits atop slow regulation like ripples on deep water. Third, the young sun is fainter in total luminosity than the modern sun, yet it is more aggressive in high energy output, so the planet receives less warmth but more chemical disruption, as if the star learns restraint in brightness before it learns restraint in violence. Only takes stellar youth for gentleness and harshness to coexist. The quiet scientific mystery here is the exact magnitude and timing of early solar activity and its net effect on Earth's atmosphere and climate. Stellar evolution models and observations of young solar analogues suggest higher ultraviolet and particle fluxes, but translating that into specific Archean Earth conditions requires assumptions about magnetic field strength, atmospheric composition and shielding by hazes or early magnetic protection. It also requires reconstructing a sun that cannot be observed directly in its youth. Only takes a missing star to make a vital forcing term uncertain. Earth's atmosphere responds in layered ways. Ultraviolet-driven photochemistry can produce organic aerosols if methane is abundant enough relative to carbon dioxide. Such hazes can reflect sunlight and cool the surface while also shielding ultraviolet, creating a feedback that can stabilize or destabilize temperatures depending on details. The haze is not a fictional veil. It is a plausible outcome supported by photochemical modelling and analogues like Titan's atmosphere in the modern solar system, though Earth's composition differs and the conditions are not identical. The story remains cautious. Haze may form in some regimes and its prevalence remains uncertain. Only takes a threshold ratio of gases for the sky to start manufacturing its own filters. The speed of light frames this feedback by enforcing a separation between cause and response. A solar flare occurs. Ultraviolet arrives minutes later. Photochemistry begins where the photons are absorbed. Aerosols form over time. Their climatic effects accumulate over longer time as radiative balance shifts. Nothing happens at once and no part of the chain can skip ahead. Even the ocean's response is delayed changes in radiative forcing alter surface temperatures gradually with thermal inertia smoothing the reaction. Only takes a chain of processes with different timescales to make the present always slightly behind the forcing. A lesser-known detail fits here with quiet realism in the upper atmosphere. Energetic particles can ionize gases, creating transient layers of enhanced conductivity that influence how currents flow and how radio-like electromagnetic phenomena might propagate, though radio in a modern sense requires receivers and transmitters that do not exist yet. The point remains. Physical ionization changes how the atmosphere couples to electromagnetic fields, and in a more active solar environment this coupling can vary more often. Only takes a charged layer to make the sky behave like a weak conductor. A gentle modern analogy appears briefly and then fades. The young sun's bursts are like distant weather fronts that arrive in layers, First light, then wind, except the wind is plasma and the front is magnetic structure, and the planet's response is chemical and electromagnetic rather than wet. The analogy is limited and then released because the real physics is already stable in its own terms. The section returns to the deeper theme. The speed limit is not just a constraint on travel, but a constraint on how quickly systems can be coupled. Earth cannot be influenced by the sun without delay. The atmosphere cannot be chemically reshaped without photon-driven steps. The magnetosphere cannot adjust before the solar wind reaches it. The young sun's restlessness, therefore, becomes a lesson in causality. It forces Earth into a world where conditions change, but only through arrivals, and where the pace of arrivals is bounded. In that bounded pace, Earth's long-term cycles still have room to operate. Weathering continues, volcanism continues, oceans circulate. The stars' flickers add variability on top, but they do not erase the planet's slower tendencies. Only takes multiple timescales to make a world both sensitive and stable. The section ends with a quiet image. Sunlight that carries high-energy photons arrives, strikes the upper air, and begins breaking and rebuilding molecules. Those changes drift downward into climate through aerosols and greenhouse balances, and drift upward into space through escape and magnetospheric interaction. Every drift has a speed. Every influence has a travel time, and none of it is instantaneous. The speed of light remains the fastest messenger in the chain, and even it arrives late in the simplest sense, always after the sun has already been what it was. Electricity on early Earth is not a technology. It is a property of air, water, and rock under stress. Charge separates in clouds, in ash plumes, in turbulent boundaries, and it recombines in brief, bright discharges that do not need observers to exist. The Archean atmosphere, with its different chemistry and aerosol loads, still supports the basic physics of charge and breakdown. When electric fields become strong enough, insulating air becomes briefly conductive and current flows. These events are local fast and yet still constrained by propagation and medium offering, another layer of speed limits beneath the cosmic one. A scientifically accepted process anchors. The section lightning is an electrical discharge that occurs when charge separation creates an electric field exceeding the breakdown strength of the atmosphere, producing ionization and a rapid current that heats air and generates electromagnetic radiation and shock waves, all of which propagate at finite speeds set by physical laws. Only takes a charged region large enough to overcome insulation, and then the sky briefly conducts. Lightning brings light, but the light is a consequence, not the driver. The discharge heats a channel to extreme temperatures, producing a flash that travels outward at the speed of light, while the pressure wave, the thunder, travels far more slowly as sound. This layered arrival becomes a familiar lesson in speed limits later, but the section keeps it in deep time. Even in the Archean, any distant observer would see the flash before hearing the sound, because light and sound move under different rules. The point is not the spectacle. It is the hierarchy the universe permits: fast propagation in vacuum for electromagnetic waves, slower propagation in media for sound, and slower still for many other transports. Only takes one storm for a planet to demonstrate that arrival is never singular. A poetic detail rests in volcanic ash plumes. In a young Earth, volcanism is frequent and explosive eruptions can loft fine ash into the air. Collisions between ash particles can separate charge, and lightning can occur within ash clouds, stitching brief bright paths through grey columns. The lightning is not a sign of life or intention. It is a sign of friction, turbulence, and charge. Only takes rock ground into dust and hurled upward for the sky to spark. The speed of light remains the ultimate limit, but in this section, it is felt through the contrast with slower signals. Pressure disturbances in air travel at the speed of sound, which depends on temperature and composition. In the Archean atmosphere, composition differs: likely more carbon dioxide and less oxygen, and temperatures differ, so sound speed may differ from modern values. The exact numbers are not essential here. The principle is sound is slower because it is mediated by the molecular collisions and its speed is set by thermodynamic properties of the gas. A scientifically accepted fact is quiet here. Sound waves propagate through a medium at a speed determined by the medium's elastic and inertial properties, and they cannot propagate in vacuum at all, while electromagnetic waves propagate in vacuum at the speed of light. Only takes emptiness for sound to vanish entirely. 3 soft ironies settle into this section's layered arrivals. First, lightning is often thought of as instantaneous, yet it is a process with steps, leaders, return, strokes, current flow, and its consequences arrive in layers, so even the fastest-looking events have internal time. Second, the speed of light makes the flash seem immediate across human distances, while the thunder arrives late enough to count seconds, meaning the same event contains both the illusion of instant and the reality of delay. Third, Earth's most dramatic atmospheric signals are loud and bright but local, while its most consequential planetary signals, carbon cycling oxygenation, glaciation, move quietly and slowly, as if the planet reserves its true transformations for processes that do not announce themselves. Only takes deep time for quiet to be decisive. The section's quiet scientific mystery is subtle and real. The frequency and character of lightning on the early Earth are not precisely known. Lightning depends on atmospheric composition, humidity, temperature, gradients, aerosol loads, and storm dynamics, all of which differ in the Archean and are difficult to reconstruct. Some hypotheses suggest lightning could play a role in prebiotic chemistry by providing energy to drive reactions that form complex organic molecules, as in classic spark-discharge experiments, yet the degree to which this occurs in natural early environments remains uncertain and is not the only pathway to complex chemistry. The story holds the uncertainty without leaning into invention. Lightning is plausible and physically supported, but its global importance and frequency in deep time remain open. Only takes one missing climate parameter to turn a lightning estimate into a wide range. Even without claiming specific chemistry, the section keeps the physical theme. Lightning is a rapid electrical event whose effects propagate at different speeds. The electromagnetic pulse radiates outward at light speed. The shock wave moves at sound speed. The heated channel cools on its own timescale. The atmosphere's ions recombine. The event is over quickly, yet its disturbances ripple outward for longer. A miniature of Earth's broader behavior where forcing and response are separated by time. Only takes a single discharge to compress a lesson in causality into a few seconds. The Archean world also contains other waves that carry information slowly. Atmospheric pressure waves from eruptions can travel long distances bending around the globe, attenuating but persistent. Ocean waves travel across basins. Internal waves move along density layers. In rock, seismic waves travel at speeds set by elasticity and density far slower than light, but far faster than tectonic drift. Each wave type is a messenger bound to a medium. A scientifically accepted fact anchors this layered messaging. Mechanical waves require a medium and propagate at speeds determined by the medium's properties, while electromagnetic waves do not require a medium and have an invariant propagation speed in vacuum. Only takes one category of wave to remind the other of its dependence. A lesser-known detail fits gently here. Lightning and other electrical discharge can produce nitrogen oxides in atmospheres containing nitrogen, creating reactive species that can be washed out by rain and contribute to chemical cycles. The efficiency of such production depends on atmospheric conditions, and in the Archean, the net contribution is uncertain, but the process itself is real in modern atmospheres and in laboratory studies. Only takes a brief high-temperature channel through air for molecules to be rearranged. A gentle modern analogy appears and then fades. Lightning is like a sudden tear in the insulating fabric of air, briefly allowing charge to equalize, except the fabric is ionization thresholds and the tear closes immediately as the channel cools. The analogy is kept small and then released. The speed of light returns in the section's deeper refrain. Even the brightest flash is constrained by travel time, and even the most dramatic electrical event cannot become a faster-than-light message. Electromagnetic waves propagate at light speed, and within relativity this is the boundary for causal influence. Yet Earth lives beneath that boundary with many slower boundaries stacked below, making the planet a layered universe of delays inside a universe of one ultimate delay. The atmosphere's sparks and storms become another way of feeling why the limit exists not as a punishment, but as a structure that turns the world into sequences rather than simultaneity. The section ends with an image that does not demand attention. A storm cloud gathers over a warm ocean. Charge separates in the turbulence. A thin leader finds a path and a bright return stroke follows. Light spreads outward at the speed of light, instantly in feeling but still governed by distance. Sound follows later, slower, shaped by air that is itself a product of deep planetary history. Between flash and thunder there is time, and inside that time there is the entire principle. Nothing arrives without travel, and the universe is built to make travel matter. Rock speaks without light, but it never speaks instantly. Stress accumulates, fractures propagate, and the resulting vibrations travel outward through solid earth as waves that obey the stiffness and density of the medium. In deep time, these waves are part of how the planet redistributes energy and informs itself of changes. A rupture in one place alters stress fields elsewhere after a delay not immediately, and the delay is written into the elastic properties of stone. In the Archean and early Proterozoic, as crust becomes more organized into larger fragments and tectonic behavior becomes more structured, the transmission of stress through rock becomes a recurring part of Earth's internal conversation. A scientifically accepted process anchors. The section seismic waves are generated by sudden releases of elastic strain in rocks, and they propagate through Earth at finite speeds determined by the rock's elastic moduli and density, with different wave types, compressional, shear and surface waves travelling at different speeds and along different paths. Only takes a brittle failure for the planet to send a message through itself. This layered wave travel becomes another lens on the speed of light theme. Light sets the cosmic maximum for causal influence, but inside Earth the fastest practical news is often seismic rather than electromagnetic, and it moves thousands of times slower than light. The planet is therefore a system where most internal changes are known elsewhere, only after minutes, hours or days depending on distance, and where the largest structural changes, plate rearrangements, mountain building, basin formation, are known only after millions of years because their propagation is not a wave but a drift. Only takes a planet made of viscous and brittle materials for causality to feel thick. A poetic detail rests in the way seismic waves can circle a world. In the modern Earth, large earthquakes generate surface waves that travel around the globe multiple times, gradually losing energy, turning the planet into a ringing body. In deep time, the details of plate boundaries differ, but the principle of a planet that can ring remains. There is something quietly physical in that rock which seems still, can carry oscillations over enormous distances, as if the planet briefly becomes a bell with no listener. Only takes elastic energy and a spherical shape for resonance to appear. This section stays slow with tectonics as a form of delayed communication. Plate tectonics, where it operates in a modern sense, is the movement of rigid lithospheric plates over the softer asthenosphere, driven by a mantle convection slab pull ridge, push and other forces. In the Archean, the exact style and onset of modern plate tectonics remains debated, yet there is strong evidence for early crustal recycling and tectonic activity. The uncertainty is not whether Earth is dynamic, it is how the dynamism organises itself early on. Only takes a hotter mantle and a weaker lithosphere for tectonics to have many possible modes. Seismic waves reveal structure because their speeds depend on the medium, and changes in speed can reflect changes in composition, temperature and phase. In modern Earth science, the travel times of waves allow the imaging of the interior. In deep time, there are no recordings, but the physics remains. If a rupture occurs, waves propagate according to the same laws, and they carry information about the rock they traverse. The accepted fact remains mechanical waves require a medium, and their speeds are far below the speed of light, while still being the fastest way solid Earth communicates changes internally. Only takes a solider for information to have to push through it rather than fly freely. 3 soft ironies settle into this section's stone-bound causality. First, the speed of light sets an absolute boundary so high that it feels almost irrelevant on Earth, yet the planet's actual experience is dominated by much slower limits, making the cosmic speed limit a distant ceiling over a world built of thick delays. Second, earthquakes feel sudden, yet they are the release of stress that accumulates slowly, sometimes for centuries, meaning the instant event is mostly a delayed consequence, finally arriving. Third, humans later detect earthquakes with seismometers and transmit alerts at near light speed across networks, yet the waves themselves still arrive at the old pace. So the warning can race ahead, while the ground must still do its slow work. Only takes a separation between information about an event and the event's physical propagation for foresight to exist without control. The quiet scientific mystery in this section rests in early tectonic regimes. When does subduction become stable and widespread? When do large rigid plates behave as they do today? Evidence from ancient rock suggests some form of subduction and arc-like magmatism early. But the hotter Earth may favour shorter-lived subduction zones or episodic overturns. Some models propose a transition from a stagnant lid or episodic lid regime to continuous plate tectonics. Others suggest plate tectonics operates early but differently. The uncertainty is not a gap in care. It is a consequence of limited surviving rocks and complex overprinting by later metamorphism. Only takes billions of years of recycling to erase the earliest plate boundaries. The speed of light theme returns through the geometry of causality. In relativity, events influence other events only within their future light cones. In Earth's crust, a similar idea exists in practice, but the cone is slower and shaped by medium. The region of influence expands at seismic wave speeds, not light speed, and it is modified by heterogeneity and attenuation. Stress changes propagate through rock, and the timescales matter for aftershocks for dynamic triggering and for the redistribution of strain. This does not require modern cities or infrastructure. It is physics in stone. Only takes finite propagation speed for a rupture to have a timeline rather than an everywhere-at-once effect. A lesser-known real-world detail fits here with a quiet precision. In some cases, seismic waves from large earthquakes can trigger small seismic events far away by transiently altering stress conditions, a phenomenon observed in the modern Earth. The effect depends on local fault readiness and wave characteristics. In deep time, similar physics could operate wherever brittle faults exist, though the specific conditions are unknowable. The detail serves only as a reminder that waves can carry influence across distance, but only after travelling, and only in forms constrained by the medium. Only takes a near-critical fault for a passing wave to matter. A gentle modern analogy appears briefly and then fades. Seismic waves are like ripples in a thick gelatin, slower and more damp than ripples in water, because the medium resists deformation and absorbs energy. The analogy is limited and then released, returning to elastic moduli density and attenuation. The section holds the idea that the planet's interior communication is a hierarchy of speeds. Electromagnetic radiation and field changes can propagate quickly, but the most common internal reorganizations are mediated by mechanical and thermal processes. Heat moves slowly through conduction and convection. Plates move slower still, yet when brittle failure occurs, seismic waves provide a faster internal messenger, though still far below light speed. The planet therefore lives under the speed of light while rarely approaching it. And the reason is not merely technological limitation, it is material reality. Rock does not allow instant rearrangement. The universe's fastest rule meets Earth's thick substance and becomes in practice a world of delay. The section ends with a quiet image of stone carrying motion. A fracture slips along a fault. A pulse of compressional waves races outward through crystalline frameworks, followed by shear waves that cannot travel through liquid, and so reveal by their absence what is molten. Surface waves roll along the boundary between rock and air. The entire planet is briefly informed, not instantly, but in minutes and hours, and then the motion fades into heat radiated away later as infrared at the cosmic limit. Even the shaking becomes part of the planet's long conversion of organized energy into dispersed warmth. Only takes a quake to remind Earth that every message ends as heat, and every heat must leave by light. The world does not turn oxygenated in a flash. It turns by accumulation, by imbalance, and by delays that stretch longer than any storm or eruption. In the early Proterozoic, the Great Oxygenation Event begins to emerge as a persistent shift in the atmosphere's background chemistry, and it does so only after enormous spans of time in which oxygen production is matched and consumed by sinks. The pace is slow enough to feel like stillness, yet the outcome is decisive once oxygen becomes a stable component of the air. The surface chemistry of Earth changes direction. A scientifically accepted process anchors. The section, oxygenic photosynthesis produces oxygen, but atmospheric oxygen rises significantly only when sources exceed sinks, including the oxidation of reduced volcanic gases, reduced minerals, and dissolved iron, and when organic carbon burial and other processes allow net oxygen accumulation. Evidence for this transition is recorded in multiple geochemical proxies, including sulfur isotope signatures. Only takes a new metabolic pathway to introduce oxygen, and it takes a planet's worth of reduced material to delay its rise. This is a story of late arrival. Oxygen's produced locally in oceans by microbial communities long before it becomes abundant globally, at least in many models. It can create oxygen oases in surface waters while the atmosphere above remains largely reducing. The oxygen does not instantly spread because it reacts quickly with reduced species. It's consumed almost as soon as it is made, and this consumption is the delay mechanism. The planet's sinks act like a hungry buffer, turning a potentially fast chemical change into a slow geochemical transition. Only takes a reservoir of dissolved iron and reduced sulfur to keep oxygen scarce for hundreds of millions of years. The speed of light appears here not as a direct actor, but as a structural reminder of what delay means in physics. The fastest messenger carries sunlight to the surface each day, providing the energy that photosynthetic organisms use. That energy arrives quickly compared to geologic processes, yet the chemical consequence, oxygen accumulation, arrives late by planetary standards because it is constrained by reaction networks and by transport between reservoirs. The causal chain contains a fast link and an extraordinarily slow link, and the slow link dominates the timeline. only takes a fast input for the world to still change slowly. A poetic detail rests in the ocean's surface where microbial mats can form in shallow waters. These mats trap sediments, build layered textures, and can create structures later preserved as stromatolites, laminated features formed by microbial communities interacting with sedimentation and mineral precipitation. Stromatolites are not myths, and not necessarily the first life, but they are among the more tangible records of early microbial ecosystems. Their layers look like quiet ripples frozen into stone, a slow piling of life and minerals. Only takes a film of microbes and time for rock to gain a texture that records biology without needing bones. 3 soft ironies settle into this oxygen story. First, oxygen becomes the gas that later animals depend on. Yet in the early world, it is almost a waste product, quickly removed by reactions as if the planet treats it as clutter before it learns its significance. Second, the sun supplies energy daily at light speed. Yet the atmospheric transformation powered by that energy takes hundreds of millions of years, making the quickest messenger serve the slowest transition. Third, oxygen is often framed as a sign of progress. Yet from the planet's perspective, it is simply a new oxidant that makes many minerals unstable and forces chemistry to reorganize, so the advance is also a constraint that closes off older chemical possibilities. Only takes a new background gas to make entire metabolisms harder to maintain. The section's quiet scientific mystery remains in the details of timing and structure. When exactly does oxygen begin to appear persistently in the atmosphere? And how uniform is the rise? Do oxygen oases exist widely before the global shift, or are they rare and localized? How quickly does the deep ocean respond, and does it remain anoxic long after the air changes? Different proxies offer different windows, and interpreting them requires assumptions about diagenesis, sedimentation rates, and basin conditions. The disappearance of mass-independent sulfur isotope fractionation is a major marker suggesting that atmospheric oxygen and ozone reach levels that prevent the photochemical pathways that produce those anomalies. Yet the exact oxygen level required and the dynamics of the transition remain active research. Only takes one proxy with multiple interpretations to keep a timeline softly uncertain. The speed of light's deeper mystery also echoes here. Why does the universe allow a fixed maximum speed for information and influence, and why does it structure causality as it does? Earth's oxygenation does not answer that, but it demonstrates a related principle. Limits and thresholds shape history. Oxygen rises only when thresholds in sinks and sources are crossed. Photochemistry changes only when ozone becomes abundant enough to block certain ultraviolet wavelengths. Climate feedbacks change when greenhouse balances shift. These are not speed limits, but they are constraint limits, and they create delayed transitions. Only takes a threshold to make a system appear stable until it is not. A scientifically accepted fact adds another layer to the oxygen story. Once oxygen becomes more abundant, ozone can form in the upper atmosphere through photochemical reactions involving oxygen and ultraviolet light. Ozone then absorbs ultraviolet radiation, altering the radiation environment at the surface and changing atmospheric chemistry by limiting deeper ultraviolet penetration. This is not immediate and not absolute at first, but it is a profound shift in what sunlight can do to air and surface chemistry. Only takes a thin layer of ozone to make the sky a different filter. The interplay with light is steady and quiet. Sunlight arrives in spectra. Photons drive photosynthesis. Photons drive photochemistry. Photons are blocked, scattered, and absorbed by new gases. Yet the speed at which photons travel does not explain the timescale of oxygenation. It only sets the pace of daily energy delivery and the causal ordering. The oxygenation timescale is set by reservoirs, the amount of reduced material available, the rate of burial of organic carbon, the rate of volcanic outgassing, the mixing of oceans, the pace of tectonic recycling. These are slow processes that do not approach light speed in any meaningful sense. Earth changes because the slow processes finally let the fast daily input accumulate into a new atmospheric state. Only takes enough time for a daily trickle to become an ocean. A lesser-known detail fits gently here. Banded iron formations become especially prominent in parts of the Proterozoic record, reflecting the precipitation of iron oxides as oxygen becomes available in ocean waters, though the precise mechanisms and environments vary and are still studied. The bands are quiet, repetitive, and vast in volume, as if the ocean spends ages sorting iron and silica into alternating deposits. Only takes a sediment to turn dissolved metal into layered stone. A gentle modern analogy appears briefly and fades. The rise of oxygen resembles filling a basin with a small inflow, while a drain remains open. Only when the drain narrows does the water level begin to rise. The analogy is limited, but it captures the source-sink balance that delays accumulation. The section ends with the sense of delayed consequence as a universal pattern. Light arrives quickly, but chemistry can delay its legacy. Oxygen is made, but sinks consume it until they cannot keep up. The atmosphere changes only when imbalance persists. The speed of light remains the fastest messenger in the story, yet the most consequential change in this segment of Earth history is a slow chemical tipping. A reminder that limits are not only about maximum speeds, but about capacity's thresholds and the time required for a planet to exhaust its appetite for change. Ice does not need to be sudden to be extreme. It can advance by degrees, by seasons that are not recorded as names, by slow changes in the balance between what arrives from the sun and what the planet reflects back. In the Proterozoic, long after oceans form and long after oxygen begins to rise, Earth still proves that its climate can tip into states that feel almost absolute, where ice covers large fractions of the surface and the ocean becomes a darker, more hidden engine beneath. The Neo-Proterozoic Snowball Earth episodes sit far ahead in time from the early oxygen transition, yet they belong to the same family of planetary behavior feedbacks and thresholds that convert gradual forcing into a new global state. A scientifically accepted process anchors the section. The ice albedo feedback amplifies cooling because expanding ice increases planetary reflectivity, reducing absorbed solar energy and promoting further cooling, while the long-term carbon cycle can modulate greenhouse gases through weathering and volcanic outgassing, allowing climates to shift over geological timescales. Only takes more ice to make sunlight less effective, and then the planet begins to cool itself. The speed of light remains the ultimate constraint on the delivery of solar energy, but in this section, it feels almost irrelevant compared to what Earth does with that energy once it arrives. Photons cross space quickly, yet the climate's response is dominated by how much of that energy is absorbed rather than reflected, and by how greenhouse gases trap outgoing infrared. The planet's surface chooses its fate not by changing the speed of incoming light, but by changing its reflectivity and its atmospheric composition. The irony is quiet. The universe hands energy over at a constant speed, and the planet decides the outcome with slow chemistry and surface texture. Only takes a constant delivery for variability to become entirely internal. A poetic detail rests in the way ice changes the light. Snow and ice scatter, sunlight strongly sending much of it back upward, and even thin sea ice can alter the ocean's ability to absorb solar warmth. In a cold world, the sunlight that does arrive can be dazzling on ice and almost wasted in reflection. The planet can look brighter from space while being colder at the surface. Only takes frozen water for the same star to feel farther away. The section remains careful about deep time. Snowball Earth glaciations occur much later than the Great Oxygenation event, but they are part of the Proterozoic's long story of constraints and thresholds. Their exact causes and extents remain topics of active research. Yet there is broad scholarly consensus that Earth experiences episodes of very extensive glaciation in the Neoproterozoic, supported by global distributions of glacial deposits and other geological evidence. The uncertainty persists in details whether ice reaches the equator in every event, how thick sea ice becomes, how open water persists if it does, and how ecosystems survive in such conditions. Only takes one missing piece of ancient ocean circulation to keep the boundary between snowball and slushball quietly debated. 3 soft ironies settle across this climate story. First, ice is simply water in a different phase, yet it can dominate a planet's energy balance more strongly than many gases, meaning a familiar substance becomes a planetary lever. Second, the long-term carbon cycle is often described as stabilizing. Yet it can also be part of slow destabilization when its feedbacks interact with changing continents and biology, so stability and tipping are not opposites. They are neighbors. Third, the escape from a snowball state may depend on greenhouse gas buildup from volcanic outgassing, while weathering is suppressed under ice, meaning the planet may need to become more chemically extreme to become physically warmer again. Only takes a frozen surface to make carbon dioxide accumulation easier. The speed of light's deeper mystery returns here as a quiet contrast to relativity explains how the limit structures causality, but it does not explain why the limit exists. Similarly, Earth system own science can describe how feedbacks amplify and stabilize, but it does not always give a single simple reason why a particular tipping occurs at one time rather than another, because the system's state depends on many coupled factors: continental positions, volcanic fluxes, biological evolution, ocean circulation, and solar luminosity. Only takes a complex system for why now to remain partially unanswered. A scientifically accepted process adds structure to the snowball discussion. Carbon dioxide is removed from the atmosphere primarily through silicate weathering reactions that consume carbon dioxide and ultimately store carbon in carbonate minerals, while volcanic outgassing returns carbon dioxide to the atmosphere. If ice cover reduces, weathering carbon dioxide can accumulate over time until greenhouse warming becomes strong enough to trigger deglaciation. This is a plausible mechanism for recovery from extensive glaciation supported by modelling and geochemical reasoning, though details and thresholds remain debated. Only takes an ice-covered continent to slow a major carbon sink. In this long cycle, the speed of light is present as the unchanging pace of the sun's energy supply. The sun is slightly brighter in the Neoproterozoic than in the Archean, yet the planet still manages to freeze extensively, emphasizing again that internal feedbacks can dominate over gradual stellar brightening. The photons keep arriving, yet the surface reflects more of them, and the atmosphere traps less of the outgoing infrared in some scenarios until the balance tips. The arrival speed does not prevent the tipping. It only ensures that the forcing is delivered causally and consistently. Only takes a constant to make feedbacks the main authors of change. A lesser-known detail fits softly here. Cap carbonate's unusual carbonate deposits. Found above some Neoproterozoic glacial deposits are often interpreted as evidence of rapid changes in ocean chemistry and carbonate saturation following deglaciation. Though interpretations vary and the exact formation processes remain studied, the cap carbonates appear like a geological punctuation mark, carbonates laid down in conditions that differ sharply from what comes below. Only takes a major climate transition to leave a distinct chemical signature at the boundary. A gentle modern analogy appears briefly and fades. The ice albedo feedback is like turning up a mirror in a room, making the same lamp feel dimmer because more light is reflected away, except the room is a planet and the lamp is a star. The analogy is limited and then released, returning to radiative balance and feedback loops. The quiet scientific mystery remains in the details of how a planet escapes. How thick is the ice? How does the ocean circulate beneath? How do nutrients and life persist? How quickly does carbon dioxide build, and what additional gases or aerosols might contribute? Even with a broadly accepted feedback framework, the specifics remain uncertain, and the geological record is interpreted through limited windows. Only takes a few scattered outcrops across continents to reconstruct a global climate story. The section ends by holding the contrast between the fastest and the slowest. Light arrives with unwavering speed, yet climate can drift and then tip over millions of years. A snowball state, if achieved, is a new global condition that does not require instant action, only feedbacks allowed to run. The speed of light remains the outer law, the ceiling that no influence crosses, while the planet demonstrates that the most powerful transformations are often the ones that take their time building from small changes in reflectivity and chemistry until a new equilibrium becomes unavoidable. Spacetime does not announce itself with a sound, and it does not carry a texture that can be touched. It is inferred from how motion behaves, how clocks compare, and how light refuses to change its pace. In the Proterozoic world, continents shift and oceans circulate, but beneath those slow rearrangements lies a framework that never negotiates the geometry that makes the speed of light invariant. This section does not leave Earth behind, it keeps Earth as the physical stage where invariant rules quietly apply. A scientifically accepted fact anchors the section in special relativity. The laws of physics are the same in all inertial frames, and the speed of light in vacuum is invariant for all such observers, leading to time dilation length contraction and a causal structure described by light cones which define which events can influence which others. Only takes one invariant speed to tie space and time into a single accounting. The limit feels less like a speed in this framing, and more like a boundary of possibility. It is the slope of the light cone, the edge of what can be connected by cause and effect. Anything that happens outside that cone cannot be influenced by the event, not because the universe is unkind, but because the structure of space-time forbids it. Even gravity in modern understanding is not exempt. Changes in gravitational fields propagate at light speed. In general relativity, and gravitational waves carry those changes outward. The Proterozoic Earth does not need to produce detectable gravitational waves for this to be true. The rule exists regardless. Only takes a universe that respects causality for even the strongest forces to obey a speed limit. A poetic detail rests in Earth's horizon. On a rotating sphere, the line between day and night moves steadily, and light spreads across the surface with the finite travel time, creating a terminator that is not a magical boundary, but a geometric one. From a mountain or a flat plain, sunrise is a moving edge, where light that has travelled from the sun meets air and dust and water, and begins scattering into colours. Even in a Proterozoic atmosphere with different compositions, the basic optics remain shorter. Wavelengths scatter more readily, and the low-angle path through air filters light into reds and golds. Only takes a long path through gas for a star's white light to become warm at the horizon. 3 soft ironies settle into this section's quiet geometry. First, the speed of light is often treated as a property of light, yet relativity makes it a property of space-time itself, meaning the limit is not a traffic law, but a structural feature of reality. Second, the most dramatic consequences of the invariant speed-time dilation and length contraction are usually introduced with fast rockets and precise clocks, yet they apply everywhere, including to a quiet rock sitting on a Proterozoic shore, simply because the rule does not wait for excitement. Third, humans search for why the limit exists, yet the limit is so deeply embedded that it becomes the measuring stick by which other explanations are framed. So the question is asked from inside the very structure that answers nothing about its own origin, only takes a foundation for curiosity to stand on it and still look below. The section stays grounded by letting Earth's slow processes echo the idea of invariant structure. Continents assemble into larger masses, break apart and assemble again, a tectonic geometry that changes slowly, while spacetime's geometry remains the quiet constant in the background. Ocean basins open and close over hundreds of millions of years, yet every electromagnetic signal in that entire span obeys the same light speed constraint. A volcano erupts, ash rises, lightning sparks, auroras flare if they do, and in each case the electromagnetic component propagates at the same limit. Earth's surface is a place of changing boundary conditions applied to unchanging physical rules. Only takes a dynamic planet to highlight how stable laws can be. The quiet scientific mystery in this section returns to the deepest theme physics describes the invariant speed through symmetries and geometry, yet it does not fully answer why spacetime has this particular structure, or why the invariant speed exists at all rather than infinite or different. In many formulations, the speed of light is tied to the structure of electromagnetism, and to the requirement that the laws of physics take the same form for observers in relative motion. One can say that if there is an invariant speed, it becomes the speed of light in vacuum because electromagnetic waves propagate at that speed. One can also choose units where this constant is one, making it a conversion factor. Yet none of this feels like an ultimate why. The universe simply has a finite invariant speed, and the deepest origin remains a foundational question that is still open to interpretation and deeper theory. Only takes a perfectly consistent constant to remain partly unexplained. General relativity adds another layer. Space-time can curve in the presence of energy and mass, and free-falling motion follows geodesics in that curved geometry. Light still travels at the invariant speed locally, yet its path can bend in curved spacetime, and time can flow at different rates depending on gravitational potential. This is accepted physics. Earth's gravity is weak compared to massive stars, but the effect exists. Clocks at different altitudes tick at slightly different rates, and precise modern technologies correct for this. In the Proterozoic, there are no engineered clocks yet. The principle remains. Time is not a universal single pace everywhere. It is part of geometry. Only takes gravity for time to become slightly uneven. A lesser-known real-world detail fits gently here. Even the rocks that later record Proterozoic history through radioactive decay chains rely on the steady ticking of quantum processes that are consistent across time, allowing radiometric dating. That steady ticking is not directly about relativity, but it depends on invariant physical laws. The ages assigned to rocks assume that decay rates remain constant under ordinary Earth conditions, and extensive evidence supports that assumption. Only takes a stable law for deep time to be measurable at all. A gentle modern analogy appears briefly and fades. The invariant speed is like a universal conversion between distance and time, not chosen by convention in the way units are chosen, but enforced by how events connect. The analogy is limited, and the section returns to light cones and causality. Earth continues to provide quiet examples of finite propagation. A storm system moves. Pressure changes travel as sound waves. An earthquake occurs. Seismic waves travel through rock. A change in solar output occurs. Sunlight and solar wind arrive later. In each case, the causal influence has a front that advances at some speed never infinite. The light speed limit is simply the fastest possible of these fronts. It is the boundary that ensures the universe is not a single instant. It gives events room to be separated. It makes before and after meaningful across distance. Only takes a finite speed for the universe to have a structure of timing rather than a single simultaneous state. The section ends with the sense that the limit is both ordinary and strange. Ordinary because it is obeyed everywhere without exception in known physics. Strange because its deepest reason is not fully known in a single satisfying sentence. Earth's Proterozoic shores, its long cycles of carbon and ice, its slow tectonics all occur under this invariant geometry, as if the planet is moving through a stage whose dimensions are fixed by a rule no actor can alter. Light continues to cross the sky at its limit, and the planet continues to change far more slowly, proving again that the universe can be structured by swift constraints while living out its history in patient time. Time is not a substance on Earth, yet Earth becomes a machine for making time visible. Layers accumulate, crystals grow, isotopes decay, landscapes rise and erode. In the Proterozoic, the planet's surface is already capable of preserving long records, and those records later become the way humans measure durations that cannot be sensed directly. The speed of light, though seemingly about distance and travel, is also about time itself, because relativity ties the two into a single structure and turns simultaneous into something conditional. This section holds time gently as a physical quantity that can be traced not as an idea. A scientifically accepted fact anchors the section in relativity. Moving clocks run slower relative to a given inertial frame time. Dilation and gravitational potential differences also affect clock rates. Gravitational time dilation. While in geophysics and geochemistry, radiometric dating uses known decay rates of unstable isotopes to measure the ages of rocks and events across billions of years. Only takes a stable decay law for deep time to be counted at all. The Proterozoic world does not carry wristwatches, but it carries uranium in minerals, potassium in feldspars and micas, rubidium in certain rocks and other parent isotopes that decay into daughters at characteristic rates. When minerals crystallize, they can lock in parent and daughter ratios in ways that later allow age determination, provided the system remains closed or can be interpreted with known histories of disturbance. This is accepted practice in earth science, and it depends on the constancy of fundamental physical interactions. The universe does not renegotiate decay rates according to mood. Only takes a weak interaction and a half-life for time to be written into stone. A poetic detail rests in zircon, a mineral that can survive extraordinary spans. Zircons can form in magmas and incorporate uranium while excluding lead, meaning lead found later can be interpreted as radiogenic. Zircon crystals can preserve internal zoning, and their cores can be older than their rims, recording multiple events. In a thin, polished section under a microscope, their growth rings can resemble a quiet map, a set of bands that were once boundaries in a cooling melt. Only takes a durable crystal to act as a time capsule through metamorphism and erosion. The speed of light enters as a different kind of clock. Because signals travel at finite speed, every observation is delayed. A view of anything distant is a view into the past. Even on Earth, the delay across room-sized distances is tiny, but across planetary and astronomical distances, it becomes meaningful. This delay is not a philosophical statement. It is a measurable travel time. The sun is seen as it was minutes ago. The moon is seen as it was more than a second ago. In modern geodesy, signals sent between satellites and receivers rely on the constancy of light speed to measure distances. The accepted fact is quiet light speed constancy allows precise timing-based distance measurements, and in relativity the speed of light links units of space and time in a way that makes it central to modern definitions of measurement. Only takes one invariant speed to turn time of flight into distance. 3 soft ironies settle into this section's quiet timing. First-time dilation is often framed as a strange effect that occurs only at high speed or near massive objects, yet it is always present in principle, and modern technologies must account for it even in Earth orbit. meaning the universe applies its subtle corrections everywhere, while most lives proceed as if time is uniform. Second, radiometric dating assumes stable decay rates over immense spans, and the success of this assumption gives humans confidence in deep time. Yet the speed of light question remains a constant can be known with enormous precision, while its deepest reason remains unknown. Third, the most reliable clocks in Earth history are often those inside minerals buried in darkness, meaning the planet measures time best in places where sunlight never reaches, while the speed of light, sunlight's pace, remains the most famous timing constant of all. Only takes a buried crystal to keep better time than an exposed surface. The section's quiet scientific mystery sits at the intersection of these ways of counting time. Physics describes time dilation as a consequence of spacetime geometry, and it uses atomic transitions as precise clocks. Yet questions remain about time's deepest nature in a full theory that unifies quantum mechanics and gravity, how time emerges, how it should be treated when spacetime itself is quantum, and how to define time in regimes where classical geometry breaks down. These are active foundational questions, and they are not settled in the same way as relativity's predictions in everyday regimes. Only takes a successful framework in one domain to reveal conceptual gaps in another. Earth provides a parallel kind of uncertainty. Radiometric ages are powerful, but rocks are not perfect timekeepers. They can be heated, altered, and reopened. Metamorphism can reset some isotopic systems while leaving others partially intact. Sedimentary rocks can inherit grains from older sources carrying mixed ages. Geologists therefore build timelines from multiple isotopic systems and careful contextual interpretation. The uncertainty is not whether deep time exists, it is how precisely a given event can be dated and how to interpret complex histories. Only takes a later heating event to turn a simple age into a layered story. A lesser-known detail fits gently here. Some radiometric systems like uranium-lead in zircon are particularly robust because zircon's crystal structure resists diffusion of lead under many conditions, while other systems like potassium-argon can be more easily reset by heating because argon is a gas and can escape. This difference in closure temperature is a practical expression of physics and chemistry, and it is how the planet offers multiple clocks with different sensitivities. Only takes one element's volatility to make a clock more fragile. The speed of light remains present in the way time itself is standardized in modern measurement. The modern definition of a meter, for example, is tied to the distance light travels in a specified fraction of a second, making the speed of light an exact fixed value in that system of units. This is an accepted metrological fact, and it shows how deeply the invariant speed is embedded in human measurement frameworks. Earth's rock clocks and human atomic clocks both rely in different ways on invariant physical laws. Only takes a constant to become the scaffold for an entire system of measurement. A gentle modern analogy appears briefly and fades. Radiometric dating is like a sandglass that begins when a crystal forms, but the sand is atomic transformation and the glass is the mineral lattice that keeps the products from escaping. The analogy is limited and then released, returning to half-lives, closure temperatures and isotopic ratios. The section remains slow with the idea that time is made visible through change, and change is constrained by both fast and slow rules. Light sets the fastest pace at which information can arrive. Decay sets steady rates that do not care about climate. Plate motion and erosion set slow transformations that structure the archive. The Proterozoic world becomes a layered record because it has both persistence and change. Continents endure long enough to build thick sedimentary sequences, yet they move and erode enough to recycle and rewrite. Under it all, spacetime geometry ensures that no message outruns light, and physics ensures that certain processes tick steadily. The section ends with a quiet image, a crystal cooling in a magma, locking in its chemistry, beginning a slow internal transformation that will count time without noticing. Above it, sunlight crosses space at a fixed speed and arrives each day warming and driving weathering and sediment transport. The planet's history is made of both steady ticks in darkness and swift photons in open sky, and the speed of light stands between them as a limit that turns distance into time and time into distance, even while the deepest reason for the limit remains a calm, unanswered question. Light is not only a messenger, it is a substance-like behavior of fields, a travelling change that carries energy and momentum without carrying mass in the ordinary sense. In the Proterozoic atmosphere, now more structured by oxygen, and in later stages by ozone photons, do more than warm the surface. They drive chemistry, they shape biological possibilities, and they carry information outward from Earth in reflected sunlight and emitted infrared, a steady outward broadcast. Yet the most puzzling part remains: this broadcast can never be made faster, and no influence can outrun it. This section lingers where the limit meets quantum ideas without leaving scholarly ground. A scientifically accepted fact anchors the bridge photons are quanta of the electromagnetic field, and in quantum electrodynamics, electromagnetic interactions are mediated by field excitations. While in relativity, the invariant speed sets the causal structure that quantum field theories respect through micro-causality, ensuring that observable effects do not propagate faster than light. Only takes a field description for light to become something woven into interaction itself. The Proterozoic Earth continues its slow transformations, but photons remain the fastest participants in surface life. Sunlight arrives, is scattered by air molecules, absorbed by pigments if organisms exist in surface waters, and absorbed by minerals and water. Infrared leaves again shaped by greenhouse gases. With oxygen present, ozone can form and absorb ultraviolet altering, which photons reach the surface. This is accepted atmospheric physics. Yet none of these processes modifies the fundamental speed limit. They can delay photons through absorption and re-emission. They can scatter them, they can convert them to heat, but they do not allow a signal to outrun light. Only takes a strict boundary for all clever detours to remain detours. A poetic detail rests in the way the sky changes its filtering once ozone becomes significant. Ultraviolet that once reaches deeper into the atmosphere and ocean surface is now more strongly absorbed higher up. The upper atmosphere becomes a region where certain photons are stopped, preventing them from driving the same photochemical pathways below. This is not a story of protection as sentiment. It is a story of altered reaction rates and changed chemical networks. The planet's surface becomes a different photochemical environment under the same sun. Only takes a thin layer of a reactive gas to change what wavelengths of light are allowed to do their work. Three soft ironies settle into this section's bridge between quantum and relativity. First, quantum theory allows behaviors that feel non-intuitive superposition uncertainty. Yet when it is formulated as quantum field theory, it respects the relativistic speed limit with strict discipline, meaning the strangest physics still obeys the most conservative causal rule. Second, photons are massless and therefore travel at the invariant speed in vacuum, yet they are also the mediators of electromagnetic force, so the speed limit is tied to how one of the fundamental forces communicates, making the limit feel less like an external rule and more like a built-in tempo of interaction. Third, the more deeply physics studies light, the more it discovers that light is not a single thing but a behavior of fields and excitations. Yet the speed remains the same, as if identity can be complicated while pace remains simple. Only takes a constant pace to unify many forms of description. The quiet scientific mystery in this section sits near the edge of modern understanding. How, at the deepest level, does the speed limit relate to the structure of the quantum vacuum and to the unification of forces? In quantum field theory, the vacuum is not empty. It has fluctuations and field structure. Yet these fluctuations do not permit faster than light signaling, and the causal structure remains intact. In attempts to unify quantum theory with gravity, questions arise about whether space-time itself is emergent from more fundamental degrees of freedom, and if so, how the invariant speed arises in that emergence. This remains an active frontier with no single confirmed answer. Only takes an apparently empty vacuum to conceal layers of structure and still keep its strict causal rule. Earth's own vacuum, the space above the atmosphere, is also not empty in a practical sense. It contains plasma fields and radiation, and it is shaped by the magnetosphere. Yet the speed limit remains. A solar electromagnetic disturbance propagates at light speed. Solar wind particles arrive more slowly. Magnetospheric reconfigurations occur after arrivals, not before. The planet's interactions are threaded by fields, and those fields still respect the same causal structure described in relativity. Only takes a field to spread influence, and it still cannot spread it faster than light. A lesser-known detail fits gently here. The transparency of the atmosphere depends strongly on wavelength, and there are windows where radiation escapes more easily, and bands where it is absorbed. This selective transparency matters for climate and for remote sensing. In quantum terms, it arises from molecular energy levels and selection rules. The planet's temperature and the sky's colour are therefore partly decided by quantum discretization. Only takes quantized vibrational modes for a planet's heat loss to become spectrally patterned. A gentle modern analogy appears briefly and fades. The speed limit is like a rule in a game that all strategies must respect. Players can delay buffer and redirect, but no move can break the maximum step size. The analogy is limited, and the section returns to the real content microcausality, field propagation and invariant speed. The Proterozoic world offers a quiet physical parallel to microcausality through its own layers of propagation. In ocean water, disturbances propagate at the speed of sound in water, and mixing spreads changes slowly. In rock, seismic waves carry information faster than diffusion, but far slower than light. In air, sound travels and electromagnetic waves travel. The universe allows many speeds, but it places a ceiling above them. Quantum field theory fits into this ceiling by construction operators associated with measurements at space-like separation commute, preventing observable influence from traveling faster than light. The mathematics is technical, but the physical point is steady quantum theory. When made compatible with relativity, does not allow a usable faster-than-light influence, even though it allows correlations and fluctuations. Only takes careful theory building to keep strangeness from becoming contradiction. The section holds the limit as both boundary and guide. It shapes how forces propagate and how information is constrained. It allows the universe to have a consistent ordering of cause and effect. Yet it does not answer why the boundary exists. The value of the speed of light is fixed in a given unit system, but the existence of an invariant causal speed feels like a deep property of reality that begs for deeper derivation. Some approaches see it as fundamental symmetry, others hope for emergence. The story does not choose a speculative answer. It leaves the question intact as a calm, unfilled space that remains even after all the correct equations are written. Only takes a stable framework for mystery to become sharper rather than smaller. Earth continues to emit infrared into space at the speed limit, and it continues to receive sunlight at the same limit. The planet's chemistry, climate, and biology, where present, operate within that causal structure without needing to know it. Light is both the fastest messenger and the strictest boundary. The section ends with the sense that the limit is not merely a cap on travel. It is the scaffolding that makes a universe with delays, sequences, and records possible. Without it, the planet's layered history might not be layered at all. With it, everything arrives in time. The motion softens, and the forward edge of the story dissolves into steadier repetition. Earth remains a turning sphere under a star, and nothing about that turning needs to be finished tonight. Light continues to arrive from the sun with unwavering pace, crossing space without haste and without delay beyond what distance requires. It touches the upper air first, then the ocean's surface, then the land where land is exposed, and it is absorbed, scattered, and turned into warmth and chemistry. The planet returns that energy as infrared, sending it outward into the dark. The exchange is constant, and the constancy itself becomes a kind of rest. Only takes a steady input and a steady loss for a world to keep its rhythm for billions of years. The speed of light remains what it has been all along, a boundary that no message crosses a limit that does not need enforcement because it is built into the geometry that holds events apart. It does not feel like a wall so much as the rule that makes walls and distances meaningful. It keeps cause and effect from collapsing into simultaneity. It allows weather waves and winds to be local before they are global. It allows continents to drift rather than snap. It allows oceans to store heat and release it slowly. It allows a planet's history to be written as layers rather than as a single instant. Only takes finite propagation for time to have room to unfold. The deepest reason for the limit remains unspoken by the universe. Physics describes it with great clarity and tests it with great precision. Spacetime is drawn with light cones, and the edge of those cones is set by the invariant speed. Electromagnetic fields carry disturbances outward at that speed. Gravity, as far as the evidence shows, respects the same causal boundary. Yet the why behind the structure stays quiet like an empty interval between notes. The question does not need an answer here to remain real. Only takes a reliable rule to leave its origin as a calm gap. Earth continues to glow faintly in wavelengths that are not seen, carrying its temperature into space. Oceans continue to move heat through slow currents. Ice advances and retreats in the long patience of feedbacks. Rock holds time in crystals and in sediments, counting by decay and by accumulation. The planet does not hurry, and the universe does not permit hurrying beyond its boundary anyway. In the end, there is only the steady turning, the steady arrival, the steady departure, and the wide quiet between them.